Hello, this is Sir Aris. Let us continue our discussion on first order differential equations. We will make use of theorems to determine the existence and uniqueness of solutions of linear and also later on nonlinear equations. For linear equations, we have this theorem 1 telling us that if you have functions p and g which are continuous in an open interval I, uh, where t is bounded by alpha and beta, containing the point t equals t sub t naught, then there exists a unique function y that satisfies the differential equation dy by dt plus p, a function of t, times y equals g, a function of t, for each t and I, and that also satisfies the initial condition y t naught equals y naught, where y naught is an arbitrary prescribed initial value. So to prove this, we simply use um, our method of integrating factors to solve or to get the solution of this equation. So this has been uh, shown in the book, so you can check that out, or you can also derive it yourself. You will find that with mu as our integrating factor, we get an expression for y, which is the solution, and mu is the integrating factor is given with this expression expressed in terms of p, and here we also have g. Now we are given that p is continuous. So that means that this p is integrable. So this term here for our mu is mu would be a function that is well defined. So mu is defined in this interval and non-zero differentiable function. Now, if you multiply the full expression, the differential equation by our integrating factor mu t, it simplifies into this expression. Now, with mu and t being continuous, then mu times g is integrable. So this term here is integrable. Also, that mu g is differentiable. So this y would, uh, this mu y is differentiable. And this mu g being integrable, so this y here would exist and is differentiable. So as a final part of the proof, since it's given that there's an initial condition which gives us a unique value for c, then that completes the proof that there exists a solution and the solution is unique for this given uh, condition, for the conditions given. On the other hand, if you have a nonlinear equation, we use a different theorem. Let's call it theorem 2, where you have function f and partial derivative of f with respect to y being continuous in some rectangle. So you can think of it as you have a t-axis and some y-axis, where if you have an origin ty, let's say that is, we just call it t and y is bounded by gamma and delta, whereas this ty here is bounded by alpha and beta. By the way, the bounds are not included in the interval. Um, there's a point t naught y naught inside this rectangle. So in some interval, this is only for the t value. So let's say if this is our t sub 0, then there's an interval t naught plus h and t naught minus h, uh, wherein As long as that's inside the rectangle, there is a unique solution of the initial value problem. The proof is difficult, so we skip it. Now let's have an example for a linear differential equation. Um, we use theorem 1 so that we show that the solution is unique. We divide both sides by t so that we can write it like this. This is our p. This 2 over t is our p, and this is our g. Okay, so g is continuous for all t, but p uh, will not take the value. T cannot be 0, so it can only be less than 0 or greater than 0. Now our boundary condition y 1 equals 2, that exists for t greater than 0. So it means that we can find a unique solution in the interval 0 and positive infinity, okay, excluding 0. Another example, let's have, this is a nonlinear differential equation. So here we have an x squared. This is our f, this term here. Now if we take partial derivative of f with respect to y, there's a 1 over y minus 1. So you have take partial derivative with respect to y of this term. That would give you minus 1 over y minus 1 squared. Okay, so here partial derivative of f with respect to y gives you this squared and this minus negative here. Okay, so these two are continuous as long as y is not equal to 1. So we omit the line y equals 1. So if you have a coordinate system, let's say an xy coordinate system, this is y equals 1, we should not, they are continuous as long as the functions f and partial derivative of f doesn't include y equals 1. Um, the boundary condition y0 equals minus 1, that corresponds to some point here. Let's say y equals minus 1. And since we only care about the x-axis here, we can create a rectangle which goes to positive infinity, x going to positive infinity and going to negative infinity. Then we can always write that rectangle where f and partial f over partial f with respect to y are continuous. So theorem 2 guarantees that the initial value problem has a unique solution in some interval. So let us talk about a certain type of differential equations called autonomous equations. This is useful in studying population dynamics. Um, this is the type of equations. Uh, this is the type of equations that you use in modeling population growth or certain phenomena affecting the population. For example, if you have an epidemic like the pandemic going on, we can use this kind of equations. So autonomous when the independent variable does not appear explicitly. For example, a very simple example, the exponential growth, where r is called the rate of growth or decline. Another simple example is when the growth rate depends on the population. So this hy here depends on the population y. We can write that as a specific example. You have the logistic equation where r is the growth rate, k is a constant, positive constant. If we set this term here as our f, then we can plot fy versus y. That gives us this uh, simple plot of parabola. And we see that there are points here where fy is 0. So this here f0 equals 0. Here f of k equals 0. These are called critical points, or we could just call them equilibrium solutions. Um, this k is the saturation level, this point here. What it means is that here, less than k, the derivative of y with respect to time is greater than 0. So the growth only happens at value k, y less than k. Above k, dy by dt is less than 0, so we don't see a growth. That is called the saturation level. Now let's try another form where we instead of positive here, we put a negative. Okay, just like this. And we replace k with t. R and t are positive constants. Okay, we set, again, similarly, we can plot. The plot goes like this. There are still critical points here. But in this case, so these are our equilibrium solutions. Yt is now called a threshold level because here dy by dt is less than 0, whereas here dy by dt is greater than 0. So the growth only happens above t. There's no growth below t. We can also combine logistic growth with threshold. Here we can consider this equation with these conditions. The plot of fy versus y is given by this. So we have three critical points or equilibrium positions and equilibrium solutions.